This video is over section 10.3, which is parametric equations and calculus. So in this particular section, we are going to take all of the parametric equations to the next step and introduce calculus involved. Here, this just illustrates a projectile and giving us a set of parametric equations here. And in this, we are basically wanting to locate the position of the projectile at a given time. So sometimes we also might want to know the slope at that given point. And this is all the same thing, which is where the calculus comes into play. So how can you find the slope at some time? Well, the way we will do that is by applying this theorem. So what we'll need to do is we will need to find the derivative. And finding the derivative involves finding the derivative of the function y with respect to time, and then the derivative of the function x with respect to time. And it's important to mention that the denominator cannot equal 0, because if it does, then this will be undefined. We can find higher order derivatives as well. So if we want to find the second or third derivative, which may be asked of you in your homework, then this is how we would find the derivative. So if I want to find the second derivative, I need to find the derivative of what we just found, and that's illustrated here. And I'll show you some examples of that. So here is our first example. We are asked to find the first and second derivative and then find the slope and concavity, if that's possible, at the given value of the parameter. So if I want to find each of these things, I notice that I am given a set of parametric equations here. So the first thing I want to do is find dy dx. Okay, well, if I want to find dy dx, that was in theorem 10.7, which says to find that, I find the derivative of y with respect to t, and then divide that by the derivative of the function x with respect to t. So let's do that now. Finding the derivative of y with respect to t is simply 4. Divided by the derivative of this function with respect to t is 2t plus 5. And you're done. That is the first derivative. I think the trickiest part of this is going to be changing your mindset in finding the derivative rather than finding the antiderivative. So now we want to find the second derivative. So the second derivative is what we just found. So the derivative with respect to time of what we just found, which is the derivative dy dx, and then we will divide this by dx dt. And this is from the previous slide. So we want to find the derivative of what we just found. So I have to apply the quotient rule. So applying the quotient rule, I have low d high, so the derivative of high, minus high d low, the derivative of the bottom is just 2. Square the bottom and away we go. Okay, so that is the derivative of what we just found. And we are going to divide this by the derivative of x with respect to t, which we have already done. It will be 2t plus 5. So now to simplify this, this all cancels out, that's 0, and this will give me a -8. Bumping this down, I end up with -8 over the quantity 2t plus 5 to the power of 3. And that is my second derivative. Okay, so not so bad. Now we are asked to find the slope at this value of the parameter. So in our third step, we want to find the slope at t equals 0. Okay, well, if I want to find the slope at t equals 0, remember the derivative represents the slope. So I'm going to take what I found for dy dx in step 1, and I'm going to evaluate that at t equals 0. So I'm going to take what I have for my answer in step 1, which is 4 over 2 times 0 plus 5, and I've just plugged 0 in here. This gives me a slope of 4/5. Lastly, I want to find the concavity. The concavity at t equals 0. Remember, the concavity is when you use the second derivative. So to find the concavity, I'm going to use the answer that I got for my second derivative, and I'm going to evaluate that at t equals 0. So when I do this, now all I'm interested in is if this parametric equation is concave up or concave down when t equals 0. So I don't care what the value is. All I want to know is if the second derivative is positive or negative at t equals 0. Well, looking at this function here, the top number is always going to be negative, -8. Great. Well, if I plug 0 in for t, I'm going to end up with a positive in the denominator. And I know that a negative divided by a positive is negative, which tells me that my function or my parametric equation is going to be concave down when t equals 0. And I have answered all of the questions required here. Here's our second example. It says find an equation of a tangent line to a curve at each given point. So basically, this is a three-part question, and we're going to find the equation of the tangent line on this slide at 0, 0. On the next slide, it's the same parametric equation, but it's going to be at a different point, and then the same thing on the following slide. So for the next three examples, if you will, we are going to use the same parametric equation, but different ordered pairs. Okay, so if I want to find an equation of a tangent line, this is information from Calc 1. Remember, we need to have a point and a slope in order to find an equation of a line. Then, once we have a point and a slope, we can write an equation in point-slope form, which is y minus y1 is equal to m times the quantity x minus x1. Well, the nice thing about this is we already have a point. The point is given to us, which is 0, 0. The thing that's going to be tricky is finding the slope. Okay, so we know that the slope is the same thing as the derivative. So if I want to find dy dx, we have learned from the previous slides that dy dx is the derivative of y with respect to t divided by the derivative of x with respect to time. So if I find the derivative of the function y, I get 2t minus 2 divided by the derivative of the function x is simply 2t. Since all of these numbers have a 2 in common, or each of these terms, I can rewrite this and simplify it as t minus 1 divided by t. Okay, so this is really important. This is going to help us find the slope. The problem is we don't know what value to plug in for t. So what we need to do is a little bit of investigating to figure out which value to plug in for t. So let's take a look at what happens at 0, 0. At 0, 0, if I plug 0 in for x, because x is 0, if I plug 0 in for x, I have 0 is equal to t squared minus 4. Okay, well, if 0 is equal to t squared minus 4, I can add 4 to the other side, so t squared is equal to 4. I know that this occurs when t is positive and negative 2. Oy, that's two values for t, and I don't know which one to plug in. So let's take a look at what happens when I plug 0 in to the y equation. If I plug 0 into the other equation for y, I have 0 is equal to t squared minus 2t. Solving this algebraically, I notice that there's a t in common, so I can factor that out. And when I do that, I can apply the zero product property, so either t equals 0 or t equals positive 2. Okay, well, now I have, let's see, 3 different possibilities here. I have either negative 2, positive 2, or 0. Well, what I want to do is find the overlap. So at the ordered pair 0, 0, the overlap occurs at positive 2. So I am going to use t equals 2 when finding my slope. So the derivative evaluated at t equals 2, so using the equation that we found, will be 2 minus 1 over 2, which reduces to 1/2. This is my slope at the ordered pair 0, 0. So now I have my point and I have my slope. I'm going to plug that into the point-slope formula as mentioned previously. So in order to find my equation of the tangent line, I will have y minus 0, because this is x1 and y1, is equal to 1/2 times x minus 0. Simplifying all of this, I get y equals 1/2 x. So the slope of the tangent line of this parametric equation is y equals 1/2 x at the ordered pair 0, 0. So now on the next example, it is the same two parametric equations, but now we have a different point. So recall from the previous slide that we found the derivative to be t minus 1 over t. Okay, so now what we need to do is we need to evaluate these two equations at this ordered pair. So at the ordered pair -3, -1, when x is equal to -3, I'm just going to plug that in now. I have -3 is equal to t squared minus 4. Well, I want to get t squared by itself, so I'll add 4 to both sides, and I get t squared is equal to 1. T squared equals 1 when t is equal to positive and -1. Okay, well now let's plug -1 in for y. When I do that, I have -1 is equal to t squared minus 2t. Well, this one's a little more complicated, so what I need to do is set this equal to 0. So I have t squared minus 2t plus 1 is equal to 0. This is an easy trinomial. Hopefully you can factor this. This factors into t minus 1 times t minus 1, which gives me t equals 1. Well, again, I want to identify the overlap, and the overlap occurs at t equals 1. So this is what I'm going to plug into the derivative that we found on the previous slide. So dy dx evaluated at t equals 1 gives me 1 minus 1 over 1, which is 0. So this is telling me that the slope is 0. So plugging it into the point slope equation, I have y minus a negative 1, which gives me y plus 1, is equal to 0 times x minus a negative 3. So simplifying all of this, I find that y is equal to negative 1 is the equation of the tangent line at the ordered pair negative 3, negative 1. Now I think you're probably getting the hang of this, so what I would recommend doing is pausing this video and seeing if you can do this one on your own, and then unpause it and see if you get the same thing. All right, so recall that we have found the derivative to be t minus 1 over t. So we're going to plug this value of negative 3 in for x, this value of 3 in for y. Turns out we've already found when x is negative 3. So again, add 4 to both sides. 1 equals t squared. So we find t is plus or minus 1. Plugging 3 in for y, I need to set this equal to 0. I always try to make the squared term positive. So I'm going to notice that this is an easy trinomial, so I'll factor this. This factors into t minus 3 and t plus 1. So t is equal to negative 1 and positive 3. As we did previously, we want to find the overlap. The overlap occurs at t equals negative 1 in this case. So we are going to evaluate the derivative at t equals negative 1. This gives me negative 1 minus 1 over negative 1, which is negative 2 over negative 1, giving me a slope of 2. So my tangent line is y minus y1, which is 3, is equal to 2 times x minus a negative 3, which is x plus 3. If you want, you can go ahead and solve for y in order to put this in slope-intercept form. In order to do that, distribute this 2, and then get y by itself by adding 3. So the slope-intercept form of this equation is y equals 2x plus 9. Not so bad. Okay, so this example is a little bit different and a little more advanced, and you kind of have to think outside the box a little bit here, because what we want to do now is find the points or the ordered pairs, if any, of a horizontal and a vertical tangency to the curve. Okay, so now let's think about this a little bit. Now, if I want to find a tangent line, we always want to find the slope. And remember, the slope is found by taking dx. The slope, the definition of the slope is dy dx. And we learned earlier that this is dy dt divided by dx dt. Okay, so this is the slope. Now, if I want to find a horizontal slope, means the line is like this. And that means a horizontal line has a slope of 0. So what would make this fraction here 0? Well, the only time a fraction is equal to 0 is when the numerator is equal to 0. So, in order to find points of horizontal tangency, I need dy dt to equal 0. On the other hand, if I have a vertical tangency, that means our tangent line needs to be straight up and down. Recall that this is when the slope is undefined. Well, if my slope needs to be undefined, the only way that will happen in this fraction here is if the denominator equals 0. Therefore, dx dt needs to equal 0. Now this information that I have here is going to be very important when we find or attempt to find the horizontal and vertical tangencies. So let's start off by finding the horizontal tangency. Now in this case, we've already said that we know that dy dt must equal 0. So the first thing we need to do is find dy dt, and that's the derivative of this with respect to time. So if I find dy dt, I get 3t squared minus 3. I can also rewrite this by factoring out a 3 and saying 3t squared, 3 times the quantity, t squared minus 1. Well, we know that this needs to equal 0. So if this is the derivative, we want this to equal 0. Well, how will this equal 0? This will equal 0 when t squared minus 1 equals 0. And this will occur when t is positive or negative 1. Okay, so let's talk through this. Now again, we want to find all of the points, and these points are ordered pairs. So I have just found that this derivative is equal to 0 when t is positive and negative 1, which means I'm going to have 2 points of horizontal tangency. One is when t equals negative 1, and the other is when t equals 1. So I need to find each of those ordered pairs. So when t is equal to negative 1, in order to find x, I'm going to plug negative 1 in there. So x is equal to negative 1 squared minus a negative 1 plus 2. Well, when I simplify that, I get 4. Okay, well, if I want to find y when t is negative 1, I have negative 1 cubed minus 3 times negative 1. Evaluating that, I get 2. These together tell me that at the ordered pair 4, 2, x and y, I will have a horizontal tangency. I'm going to do the exact same thing at t equals positive 1. So in order to find x, I'll have 1 squared minus 1 plus 2. Evaluating that, I get 2. Then y equals 1 cubed minus 3 times 1. Evaluating that, I get negative 2. Putting these together, I find that at the ordered pair 2, negative 2, I will have another horizontal tangency. Okay, we have found each point in which we have a slope of 0 for a horizontal tangency. Now we're going to find a vertical tangency. So we talked earlier and discovered that in order for a vertical tangency to occur, dx dt must equal 0. So if I find the derivative of x, I find that dx dt is equal to 2t minus 1. Well, I want 2t minus 1 to equal 0 in order for this vertical tangency to occur. And so then I discover that t is equal to 1/2. So there will only be one place where there will be a vertical tangent line, and that occurs at t equals 1/2. So I need to find that ordered pair. So in order to do that, at t equals 1/2, x is found by plugging 1/2 in anywhere I see a t. And when I do this, I end up getting 7/4. I will do the same thing for y. Plug 1/2 in for y anywhere I see a t. And when I do that, I get a negative 11/8. So not great numbers, but they'll do. So at the ordered pair 7/4, negative 11/8, I will have a vertical tangency. So I have found all points in which there is a horizontal and vertical tangency to the given curve. We're now moving on to arc length in parametric form. We have found arc length in other forms, but now we have parametric form. And quite frankly, it's not terrible as long as you follow this given formula here. Well, either of these really. I suppose I'd prefer this one because it specifically says dx dt and dy dt. So basically you find the derivative of each equation, square it, and integrate it. This will lead us to a cycloid, and we will talk more about these fancy pictures in the next section. But let's go ahead and see an example of finding the arc length. So here it says find the arc length of the curve on this given interval. We need the interval for our limits of integration. So the formula from the previous slide is the following. S is the antiderivative from a to b. Now notice we're finding the antiderivative instead of the derivative. So you're going to be going back and forth a little bit in this section, which sometimes leads to confusion. Oops. So the formula is the following. Okay, so in our case, we need to find the derivative of each of these. So I'm just going to jot that down up here. So dx dt, the derivative of the function x with respect to time, is simply 12t. And then dy dt is 6t squared. So I like to find the derivative of those separately and then plug it into our formula as needed. So this integral becomes the integral from 1 to 4 of the square root of 12t squared plus 6t squared squared dt. So we have a lot of simplifying that's required. After squaring each of these, I get 144t squared plus 36t to the 4th power. All right, well, I notice that these two terms have a 36t squared in common. So I'm going to rewrite this as the square root of 36t squared times t squared plus 4. I'm just rearranging that a little bit, dt. Okay, well, remember, according to different algebraic properties, with multiplication, I can take the square root of this and the square root of this separately. So this becomes the integral from 1 to 4 of 6t times the square root of t squared plus 4 dt. Okay, well, here we need to integrate this. And what I would do is use a u substitution. So in order to do that, I would let u equal the radicand, so t squared plus 4. So if u is t squared plus 4, then du, is 2t dt. Okay, well, in order to simplify this, I'm not going to go into a lot of time to show you the steps of this in this video. You should be able to. So I'm going to kind of wave my hands a little bit and tell you that you should end up with 2 times the quantity t to the 4th plus 4 to the 3/2 power. And you will want to evaluate that from 1 to 4. Okay, so from here, if you want, you can plug it into your calculator. There are a couple different ways you can go about solving this algebraically. I'm going to take that 2 out. If I plug 4 in, I'm going to have 20 to the 3/2 power minus 5 to the 3/2 power from plugging in 1. Well, continuing to simplify this, you can write this in the following way if you'd like. This will become 2 root 5 quantity cubed minus the square root of 5 cubed. And if you simplify this a little bit further, you have some like terms. This is really 8 times the square root of 5 cubed. So we'll have 2 times 7 root 5 cubed. Oops, this is cubed here. Continuing on, 14 times the square root of 5 cubed. And this is just a lot of work. This will end up simplifying to 70 root 5, or approximately 156.525. I don't know what answers you'll be asked to find in your homework. If it says the exact value, you will want this. Otherwise, you can give the decimal value. Okay. There's one more type of problem that we will see in this section, and that is the area of a surface of revolution. So we have, again, before found the area of a surface of revolution. The thing that's different now is that we will have parametric equations. So the equation, hopefully you'll notice, is the same as arc length, but now there's a little twist of adding this 2 pi here and then whatever the function is, depending on if we're revolving about the x or y axis. So here, this is just kind of telling you how to remember the formula, but I already kind of mentioned that. So let's just move on to the example. Here's our final example. It says, find the area of the surface generated by revolving the curve about the given axis. So we want to revolve about the y-axis. So in this case here, we have our parametric equation. We need to figure out which formula we want to use. So in this case here, now we're going to use a big S instead of a lowercase s from arc length. So big S is equal to 2 pi times the integral from a to b, so we'll use this interval here, of f of t times the square root of the derivative of x with respect to time plus the derivative of y with respect to time squared. And here, x is equal to f of t. So if we're revolving about the y-axis, we are going to plug x, the equation for x, in here. Okay, so in order to do this, we need to find dx dt, which is simply t squared. And we also need to find dy dt, which is just 1. Ooh, fantastic. Okay, so plugging into this formula here, s is equal to 2 pi times the integral from 1 to 2 of f of t. Now remember, that's just x. So in our case, it's going to be 1/3 t cubed times the square root of dx dt is t squared. Oops, we got to square that also. So t squared squared plus dy dt is 1 squared. Well, from here, you might want to take this constant of 1/3 and move that out in front. So, and simplify things a bit. So when you do that, you have 2 pi over 3 times the integral from 1 to 2 of t cubed times the square root of t to the 4th plus 1 dt. Again, we'll want to use a u substitution. So I'm going to let u again equal my integrand, my radicand, the value under the radical. So t to the 4th plus 1. So du is 4t cubed dt. So here we need a 4, so I'll put a 4 in here, undo it with a 4th over here. I'm going to wave my hands once again and tell you that you should end up with pi over 9, once simplified, times the quantity t to the 4th plus 1, all raised to the power of 3/2, and then we will evaluate that from 1 to 2. I think you guys can plug these values in. So when you do, you're going to have 2 to the 4th plus 1 to the power of 3/2 minus 1 to the 4th plus 1 to the 3/2. Keep going, and you should end up with a decimal of approximately 23.48. And this concludes section 10.3.